It's great to be part of this wonderful program. And so far, I enjoy very much the program, and great to be part of that. So my assignment was on big data finance, but I equally is as enjoyable to apply, big data analytics into other areas such as genomics and different kind of disease. Okay. So this is the outline of my talk. I'll give introduction. Like Steve, I'll just set the tone for my own talk. And because I have been doing this kind of things, right, for over 20 years, so certainly we built a lot of products. I'll give you a broad overview because otherwise I'll be too much spread all over the place. So in particular, we developed a 2R software package, one called FarmSelect and the other called FarmTest. So all farming really means factor-adjusted, robust model selection, factor-adjusted, robust multiple testing, factor-adjusted, regularized modeling, or factor-adjusted risk modeling. So all farm depend. All these kind of things, right? And then I'll talk about robust prediction, augmented factor models, and factor adjusted robust model selection. So this is the outline of my talk. Let me begin with introduction. And my talk today mainly focuses on dependence and heavy tails, and other issues of big data I'll talk later on. So let me just set a tone on data tsunami, right? So information technology has revolutionized the data collection process. So millions of surveillance video cameras and billions of internet searches and social media chat and tweets produce massive data that contain vital information about security, public health, consumer preference, business sentiments, economic health, and many others. And similarly, like billions of prescriptions, enormous amount of genetic and genomic information provide critical data on health and precision medicine. So nowadays, big data is everywhere, right? So from business to internet to engineering, biological science, even digital humanities, right? So they certainly have huge impact on systems like storage, communication, and computation architectures. At the same time, they have huge impact on analysis, like statistical computation, optimization, and privacy, and so on. So, to me, what is data science, right? So the collective efforts trying to solve these kind of challenges, right, engulfed by the applications, surrounded by all the applications, is what we really now understood as data science, right? So at least it consists of data acquisition and storage, data analysis, scientific computing, in order to make sound and optimal decisions. So now, since we are talking about, data science, right? So at least we need to know what are special features to the data science. And to me, there are at least 5. I address different kinds of things at different occasions on different time. But today, I'll focus on dependence and heavy tails. And of course, there are huge spurious correlations. There are heterogeneity. This is very challenging issues. And endogeneity. Sophia and Jianqing both touch a little bit on these a little bit. So today, I only focus on these 2. And let me begin with examples, right? So this is a very typical example. You want to forecast something. In this case, is U.S. bond, U.S. government bond risk Premia, and let's say maturity would be 2 years, 3 years, 4 years, and 5 years. So you could think of 4 outputs, or you could just think in each individual time series you want to forecast. And what is available data to you? So in this case, I denote by XT is 131 disaggregated macroeconomic time series. And so this is disaggregated. And at the same time, I have 8 aggregated macroeconomic time series, right? So they're different at different scales, right? So one basically is a summary of the other, if you like, right? Oh, and you see this is something that I changed this morning. W1 is linear combination of 5 forward rates. W2, GTP, right, and so on. W8, consumer price index, right? Just to give you an idea what those are. right? And now let's look at the kurtosis of those 131 macroeconomic time series. Right, so for each individuals, I could calculate kurtosis, and I calculate those. So this is the distribution of the kurtosis I have. So among those, just like Sylvia said this morning, Gaussian no longer applies. Right? So there are 43, a third of those have a heavier, tail than t-distribution with degree of freedom 5. And this heavy tail is evidence. Right? Some of those even have kurtosis around 40 or 50. Right, so, and at the same time, as you know, standardized feature in financial time series is their heavy tail. So now the question for this particular problem I'm asking is two, right? How do we handle heavy tail data, right? The second one is, in typical applications, you are not only endowed by the data, like a microarray data, you are also being endowed with clinical information, like my WT here. So how do you use those covariates to advance your study of big data issues, right? So of course, this is not as big as I would like to, but the concept apply to all other things. So the second example is RNA sequence data. So in this case, I have 104 autism patients and controls. And after pre-processing and so on, so you have 19,000 after you do log transform. And then I just calculate how many of those have heavy kurtosis, right? So, there are 383 have heavier than t-distribution with degree of freedom 5. And some of those kurtoses could be as big as 100, right? So this example just showed that when you have tens of thousands of variables in hand, by chance alone, some of those variables have, would be heavy tail in high dimension. So this is just by chance alone. So I have more example. Again, 1/3 of protein expressions will have heavy tail even after log transform and so on. But I think my story should stop here, right? Now the question is, how do we deal with, right? So when we do like microarray measurements, they are measured about your genomic expression, about your health. When you have 131 macroeconomic time series, you are measuring some kind of economic health. So these measurements are correlated and heavy tail. So how do we deal with this? Right? So we introduce what I call farm products or factor adjustment for something. So the first F is factor, second is adjustment, and so on. Right? So this is a common model people use for modeling dependence, the factor model, right? So you observe, let's say, macroeconomic time series, 131 of those. So they are invisible hand latent factor Ft, and B is your factor loadings plus idiosyncratic components. So in other words, typical we say noise, right? Now be decomposed into two parts. One part is the common factor. The other part is idiosyncratic part. And of course, in terms of component, this is what the component looks like when you write down as components. And this kind of application is no monopoly in time series, right? So in this case, there could be 131 time series. So the T index, right, and the time, and then this index, let's say 500 stocks, and so on, right? So J also could index number of genes, 20,000 genes, and I could be index number of experiments. And the same with fMRI. Monse was talking yesterday, right? So it could be voxels, and the I could be index number of brains. So certainly this kind of factor model is commonly used model people use to adjust for dependence. And so now let's talk about factor adjusted regression. So the first one, actually we used a couple years ago, and I'm not going to get into it, but basically thinking there's latent factor that drive all those covariates, like 131 macroeconomic time series. At the same time, these latent factors drive the outcome, such as the bond risk premia. Right, so you can build in the index in between, so this looks like a deep learning with 3 or 4 layers, depending on how you count it. Right, so this is, in this case, would be a linear regression, and this is the same model that Jiwei was talking about. So this is really factor-adjusted, robust, prediction. And so in this case, right, you could extract latent factors from those 131 macroeconomic time series, and then plus your augmented variables, you have 8, right? So you could run regression one way or the other. That would be one possibility, and we did have a paper a couple years ago doing this, and this is similar to what you were talking about. So the other one is factor-adjust model selection. Actually, this is the part I'm going to focus a little bit today. So you have outcome, like bond risk premia, and you have 131 macroeconomic time series. And those macroeconomic time series, they are driven by certain latent factors. So therefore, they will make all of your covariates highly correlated, and the traditional theory on lasso, scarce, and so on will break down, right? And then the factor-adjust model selection is very simple. Very simple. So by decomposing your X into common part plus latent part, common part plus idiosyncratic parts, and then you just substitute this into blue X, right? So you get a model like this. So it's just a very simple substitution. So now if you look at this, so what is the new variable? The new variable is the common factor Fi, and the plus idiosyncratic part, right? So by including a few more common factors as your predictor, so by lifting your space, let's say suppose it's 5-factor models, by lifting your space five-dimensional more, right? So now all covariates suddenly become weakly dependence, right? Because all those idiosyncratic part will behave like what you would expect. They are weakly correlated. And this Fi, by definition, uncorrelated with Ui, right? So then the regularized method, will work, right? And this one we program in R called FarmSelect, factor-adjusted, model selection. So really, which really basically saying, hey, you infer or you learn latent factor plus factor loading from the data. And once you learn this from that, then you have idiosyncratic components too, right? Now you use your idiosyncratic part plus factor parts as input variable. By lifting space a few more dimensions, all covariates suddenly become nearly independent. So this is the FarmSelect that we are going probably later on going to talk a little bit about that. And this is just a simple example to illustrate that, right? So this is sparse linear model. So I have 10 non-zeros, and the remaining are zeros, right? And then xi are coming from equicorrelated covariance matrix. As correlation getting bigger and bigger, if you apply directly the lasso kind of methods, so the number of variables you select also increases with the underlying correlation of the sigma. And on the other hand, if you do factor FarmSelect, right? So by lifting space just one more dimension, because there's only one latent factor here, right? So by lifting dimension one more factor, in this case, you increase dimensionality from 250 to 251 using your latent factor plus idiosyncratic part as regression. So your model size, select model size consistently about 10. So in terms of model selection consistent rate, so we are nearly 100% correct, and lasso nearly 0 as dimensionality increases. So this shows really the power of lifting, right, of factor adjustment. And here, I just would like to note, right, the beta you want in this sparse linear regression is the same beta you want in this lifted or factor adjusted model regression, right? So therefore, by just running lasso, adding one more dimension or a few more dimensions, you are really estimating the beta that you want. So it's a very cheap way of running that, right? Okay, so if you think that what I'm doing here is non-convincing because the covariance matrix here equal correlation is unrealistic, so we just doing covariance matrix is calibrated to SP500 components of the data from 80 to 2012. And now we use our factor-adjusted model selection. It's more or less, again, 100% correct, choosing the correct model. On the other hand, the lasso is this guy, right? So model selection consistent rate is very low, and then, of course, elastic net doesn't improve very much. Scat doesn't improve very much. The reason is just covariance too strong. And similarly, in terms of prediction error, right? So prediction error increases with, with the wrong model selection. So this is one piece of components on model selection. Just by doing factor adjustment, you'll improve a lot. Now here I'm talking about multiple testing. Again, I do multiple testing. Doesn't have to be in finance context. In genomics, probably has been very widely, widely used. You keep asking, has this gene been altered between treatment and control? Has this gene been altered between treatment and control? You ask it 20,000 times. The same way I ask, does this mutual fund has alpha? Does that mutual fund have alpha? Does the mutual fund have a skill? So I asked tens of thousands of times, right? So because of herding effect, because of other things, even after you do factor adjustment, common market risk factors, they still have, they could still have latent factors that drive the dependence among mutual fund performance. And so this is the factor model that we are writing. So one naive method is you're just calculating individual sample averages, right? So you get individual sample averages. And the bad thing of this is now these test studies are dependent. So when you control false discovery rates, the false discovery rate is not the one that you really want. And then when you do sample average, you regard these two components as your noise. So you're getting a bigger noise, right? So when I do factor adjustment, I learn the latent factor and idiosyncratic component, and I subtract those out. Now my noise is weakly dependent. Now my noise is reduced noise. So I would do much better, right? So this is just one simple example to demonstrate by doing factor adjustment, you'll get much better power and the size control. And this is really just factor model, as we expect. And these just are simulated parameters. And in this particular setup, I assumed I have 100 microarrays and 500 genes, right? Just imagination. And in this case, I have, a quarter of those are difference expressed, and 3/4 of those have no expressed, right? So if I, based on my observed X, I just calculate sample mean. This is the sample mean, 500 sample mean you get. You cannot see the bimodal nature of these because I have big noise. Now, if I do factor adjustment by subtracting this part out, and now I calculate sample average, the noise being reduced, you can see bimodal. Now the distribution I have here is T distribution with degree of freedom 3, so I'll introduce a robust version, and the robust version certainly separate even better. And then we, of course, doing everything here for you. It's very simple to use, right? So it's called factor adjusted multiple testing. So you basically adjust the factor first and do multiple testing. You are not only control the false discovery rates correctly, but also increase the power of your test, or misdiscovery rates. And then, of course, factor model can be used in like row rank plus sparse. We have been doing this for over past maybe 10 or 15 years, right? So you can use this to do like a risk modeling, right? So the factor implied volatility would be, right, the common part plus idiosyncratic part. So it would be a noise reduction. You could do using this to do graphical modeling and so on and so forth, or for portfolio. Selection and portfolio location. So we should have write a program for this called FarmSelect, but we didn't really get a chance to do that. And then the last part of factor is very useful and wonderful, is matrix completion techniques that is really about factor. Right? Matrix completion technique is all about factor models. So matrix completion techniques can be used in high-frequency finance. So one of the very important challenge in high-frequency finance is that stock is not synchronized traded. So therefore, you could regard it a matrix of observation with a lot of entry missing, right? So with a lot of entry missing, and then you could just use matrix completion technique to fill up these missing entry, and therefore you could use high frequency data. And in this illustration here, I basically telling you what is the most challenging cases, right? Is in high-frequency finance. So you have liquid assets. Liquid asset, there's no problem because there are a lot of data. Synchronization is relatively easy. The most difficult is illiquid against illiquid, right? So asking to slow poke to trace synchronize, right? You waste a lot of data. And it's easier just using these three pieces and then plus this low rank structure to infer these missing pieces. So matrix completion technique can be applied to high frequency finance too. So again, this is very quick drive-by on the last few years, our development on the application of factor model into different kind of financial applications. So now let me talk about how do we do, robust prediction, robust principle. And it's very simple. And this is one line of work that we did very early. So suppose that we have IID data, and we have IID data. And I do not assume it's normal, just like Sylvia said this morning, data is not necessarily normal. And I do not know that the data is symmetric, right? So I just truncate my data at certain high level tau, okay? So this, in other words, you keep when it's less than 3 standard deviation and truncate when it's above 3 standard deviation. And this is actually related to what I talked to Nancy last night. So the paper was written in 2012, and it's published in 2017. It looks like pretty bad. So anyway, so we basically saying this, right? So when you do high-level truncation, square root n times the standard error of your data, right? So this is individual, just one unit vector, right? So unit vector, IID, most fundamental with mean mu and standard deviation. So if I truncate my data at square root n times the standard deviation, what's going to happen? So the sample average based on truncated data deviate from population average, t standard error away, would be, exponentially concentrated. So in words, so even though the data was not normally disputed, by doing truncation, your sample average behave pretty much like the sample average of normal data, right? This is sample average of normal data would be still normal, we have this kind of property. So, so this is the power of truncation. By doing truncation, suddenly you make your sample average behave the same way as if the data was sampled from normal distribution. On the other hand, if you don't do truncation, that's equivalent to say taking tau equal to infinity, and the worst scenario you have would be t distribution with degree of freedom 3 or 2, 3, right? So the tail will behave like t distribution with degree of freedom 2, right? And this first property is very fundamental in high-dimensional estimation, because high-dimensional estimation, essentially, we do millions, if not billions, of sample averages, right? So give you an example. So if you are interested in high-dimensional covariance matrices, and without loss of generality, I assume equal to 0, just for me easier to write down. So you are estimating p squares of this covariance matrix, right? So now I could just apply sample mean, truncated sample mean every time. So then I got the truncated sample covariance matrix, and you could easily see that these covariance inputs, even though the data is not from normal distribution, would behave pretty much like a sample covariance matrix for normal distribution. So you only increase logarithmic order of your dimensionality, right? So this is, again, but just by doing a very simple principle of truncation, just truncate your data at high level, square root n of your standard deviation. The whole behavior very similar, like as if you have Gaussian data, as if you are working on the Gaussian data. And that's really very fundamental in many of application, downstream application of that, because this is robust covariance matrix would all become robust random matrix theories and so on. So removing auto Gaussian away. So now sometimes truncation is very easy for the data, but sometimes also for regression cases, right? So it's easier also to truncate the loss function. So this is Hilbert function, Hilbert loss, right? So would be the Hilbert loss you truncate at a certain level tau, and this is certainly more. And then you just calculate the mean of this Hilbert loss, and this mu tau would be certainly have the same concentration property as we have seen before, and at the same time, it would be more convenient when you run regression. And again, this tau differ from traditional Hilbert, which assume error typically symmetric, contaminated. So he could take any tau, be unbiased. For me, what I have in mind is I estimating xi squared, right? So my distribution, no matter what, is asymmetric. So therefore, my level of truncation tau had to be high in order to reduce the bias. So this is a very simple truncation principle. You have got in Gaussian concentration by just doing a very simple trick. Now, can we see this in action of, let's say, high-frequency finance? Yeah, so being in New York, of course, from time to time, there are always people from hedge fund asking you this, right? So in this particular case, we were given 365 signals, covariates, and we want to predict a predictable target in the future, and the target is really just a price move from current price to maybe next millisecond or next 5 ticks. And the signal is really obtained from historical data, is, let's say, the moving average or how the first few moments in the past, let's say, 10 seconds, and so on. And then our interest is how well we can forecast this, right? So we do ourselves this semester by using, deep learning techniques, and we certainly know very well what are those now the targetable target is. And this is really for that particular example, I have 83 days, so about 4 months of data. And this is already 500,000 observation or 1.8 gigabyte of data. So you could imagine I have 10 years of this data. You could imagine I have 1,000 of those stocks. Right? Everything scaled up quickly. Right? But anyway, this is the target you have, and this is 365 signals. So if I calculate marginal correlation between signal and targets, each individuals are pretty weak. Correlation maybe around 0.1, right? So this is both basically say marginal correlation very weak. Now, if I do truncated data, truncated X variable, and then truncate Y variable, and trying to find a more robust regression between X and Y. So this is the result we get, right? So I truncation starting from somewhere, let's say 1.5, you got the outer sample R squared, 1.6, and so on, right? If I do truncation to be infinity, of course, it's go back to least squares, right? So meaning that you are not truncating anything. So the least square give me a benchmark of outer sample R squared about, when you combine all those signals together, is 0.1, which is pretty good, right? So if your individual be 0.01, right? So this is very good, right? So by doing this truncation, we find optimal location. Optimal truncation in our case is 1.78 standard deviation to truncate, and multiple R squared improved by 0.4. And so the people there are pretty happy. And we do truncation for other statistical model, more complicated model too. So at the end of the day, your learning sample is more robust. At the end of the day, you're getting a better forecasting. So this is just a quick way of illustrate power truncation. I could also illustrate the power truncation by using forecasting US bond risk premia. So this is the repeat of what the data we have before, right? So YT is bond risk premia, would be 2-year maturity, 3, 4, 5, right? And XT is 131 macroeconomic time series. WT is your 8 aggregated macroeconomic time series. And then the typical way of doing principal component regression, Jiwei was talking about, and my colleague Mark Watson, called diffusion index, basically say, hey, from 131 macroeconomic times, disaggregate macroeconomic time series. You extract, let's say, latent factors. Let's say 5 of those latent factors. So now I run augmented principal component regression, right? So I have 5 latent factors plus 8 augmented variables, 8 macroeconomic time series. So I have 13. So I could just do simple linear regression to forecast bond risk premia. And this side is just the usual conventional least square. Give out of sample R square is 23.9. By just optimally tuning your truncation parameters, you jump to 37.9. And similarly, for 3 years maturity bonds, you jump from 21 to 32.6, and so on. Right? So this shows you another time the power of truncation. And it's a very cheap way to implement and a very easy way to do it. Now there's another issue, right? So when we extract latent factors, either from genomic information or from macroeconomic time series, right? So we always have augmented variable there, right? So in particular case, I have 8 aggregated macroeconomic time series, right? So this is the model, right? So this is the traditional factor model, and I do not know what this latent factor is, but somehow I know the latent factor can be partially explained by your macroeconomic time series. So in other words, it can be written as part can be explained, and plus some small idiosyncratic part cannot be explained by those latent factors, right? So example including, let's say, pharma French factors in finance, or those 8 aggregate macroeconomic time series that should be related to these latent factors that drive common dependence among those 131 macroeconomic time series. So now how do we use this covariate information? Again, it's surprisingly simple. So how do we do this, right? So for each disaggregated time series, or for each genes, whichever you will have, right? And WT is your aggregate time series. So you do non-parametric, some kind of smoothing, fitting, right? So you regress your time series on XT, and then you get your fitted value, right? So for each 131 disaggregated macroeconomic time series, you regress on those 8 aggregate time series, and you got your fitted values. Right? So if you are doing genomic information for each RNA sequence data, for each particular gene expressions, you regress on clinical information, and you get your fitted value. Right? So this is your fitted value you have there. And now it just run the principal component regression based on X hat. Right? So I trying to change notation. I was not successful rather than Y hat. Right? And why this actually improve, right? So by doing this fitting, why improve, right? And this is very simple one line of mathematical equation. So these are the model that I have. This is traditional factor model, and now I say factor can be partially explained by X. So now I do projection, right? So I project the XT condition on WT. So if this UT is exogenous, so there will be B and the EFTW, right? And now FT is written like this. So given W, I have only this W left, and this guy just by definition will be 0, right? So I got this model. Now if you compare this model, this is now my new input, and this is now my latent factors. Compare with this model, what you get, right? So I just have no terms, right? So it's the same, you still have factor model. If you are able to calculate this projection theoretically, then this projected data, projected covariance X, project data, is become a noiseless factor model, right? So compared with this line of equation, you have noise here, right? So once I do projection, you have noiseless. So then actually you increase the signal, and therefore you get him better fitting on those Bs, right? So here a few lines of detail, probably is not important. Basically saying, all right, you compute a high-dimensional covariance matrix using your fitted data, and now you pretty much proceed the same way as you do principal component analysis, right? So you calculate, leading eigenvectors. You project your data on leading eigenvectors. This is your latent factor, and so on and so forth. So it's pretty much the same, right? So here is the illustration of that particular example. So how do I do projection, right? I would do sieve basis, right? Additive sieve basis for my regression. And the only difference is that I apply, adaptive Hilbert, right? So I do truncation on my loss function here, right? So quadratic and linear outside. So I do truncation on my loss function here, and this is just sieve basis. So once you do this fitting, you get your fitted value. Now I compute the sample correspondence of my fitted value, and now I get the principal components analysis based on my fitted value, and that actually is much lighter tail. So this is really the example. If this is the kurtosis of my fitted value, right? So which it has much light tail than what you have seen before. So this is really just saying that you do projection and run principal components, you're getting a much better results. And all these kind of things, you can derive econometric theory to illustrate that. So I'm not going to get to the detail, but the idea I want to mention here is what is the truncation level of the loss function is really a trade-off of two things, right? The bigger the truncation level, the more you get into the tail, right? So you rely on more, so you are less robust. And on the other hand, if you are if alpha t is very small, you are very robust, but you create bias. So it's really a bias and the robustness, trade-off between these two. So now if I apply this technique to forecasting bond risk premia, so what's going to happen, right? So again, here is a few methods you can truncate. You can extract latent factors. One is conventional, right? Conventional means that from 131 disaggregate macroeconomic time series, I'm creating a latent factor, and this latent factor is really at aggregator level, right? Now this, let's say I create 5, and this 5 plus original 8 give me 13 variables. So I am going to regress my bond risk premia on these 13 variables. And the other one is conditional, the new one that we have, right? So I use, I do smoothing, right? XT smooth on WT first, and then I take an FT from this smoothed, or projected data, and then I just regress my outcome on this conditional type of PCA or projected type of PCA, and this will be two different methods. So this will be the potential forecasting if you really focus yourself on the linear model, and this is what I'm going to focus. So on the linear model, what is the XT I could use, right? So most lazy one, I just use those 8 macroeconomic time series. Traditional ones say augmented principal component regression or augmented factor models is you're using latent factors plus 8 macroeconomic time series, right? And then the third one is I do this FT, the projected PCA, extracting this latent factor, which use both information of WT and XT. And then lastly, I could use both of those, right, plus augmented variable and so on. And you can do nonlinear regression and so on. So, and this is the results. I just want to show you, seeing that the robustness and augmented, how it works, right? So this is the most traditional one. That's you extract latent factor and plus 8. This is augmented principal component regression. And this is by using just, you do smoothing first and do principal component analysis to extract the factor. That's one I call FT. That's making your multiple R square, outer sample R square, to be 32.6%. And now, if you do robust implementation of the same technique, you jump to here, you also jump to here, right? So the robust projection version of implementation, so you can see both actually help. For 2 years, the same, right? For 2 years, the same. And from here to here is just traditional versus the new one that we have. Okay, so now the last one, I just want to say, again, go back to the model selection issues when you have highly correlated covariates. And the reason sometimes we like this is when I do principal component regression, right? This latent factor, FT, this FT, have difficult to interpret because it is an index, a diffusion index. So you do not really know what it is other than an index, right? So when I do FarmSelect, I now get in the variable I want, right? So if you do linear combination of genes, I mean, it's very difficult to understand what that means, right? But if I select a gene, it would be more useful. So this is factor-adjusted, regularized M-estimation, or factor-adjusted, regularized model selection, whatever it is, or FarmSelect, right, that we have. So this is, the idea again, right? So this is your factor model for model dependence. And now you have linear predictor to predict outcome, right? This could be logistic regression, could be generalized linear model, could be supported vector machines, whatever you name it, right? And now I just substitute this into this X, right? So in other words, writing X as a factor part plus idiosyncratic part, or common factor part and idiosyncratic part, right? So now my new predictor, instead of using original Xi's, now I lift in space a few more spaces, right? Latent factor plus idiosyncratic part. And by construction, latent part, these two are uncorrelated, right, by construction. And the idiosyncratic part, by assumption, should be weakly correlated. So you are doing, the decorrelation, right? So now you can, this method can be applied to generalized linear model, can be applied to generalized M-estimation. So the idea, the detail is not important. The idea is by including just a few latent factor into your regression, we decorrelate the variable, and the beta you want, right? The beta you want here is really just coefficient in front of your idiosyncratic components, right? No more, no less. This is exactly you are selecting the variables, right? So this is regularized estimator, right? So this is the loss function, general loss function, linear combination, y, and this would be the regularization. This is the regularized M-estimation. So in our FarmSelect framework, we decompose X into latent factor plus idiosyncratic part, right? So you're running this model selection. And now, of course, you need some conditions, right? So you need some kind of pervasive factor models, so you need a factor to be pervasive, or the variance components of this sigma had to be, spiked. So we wrote a paper in 2015, actually published in 2017 in Annals of Statistics. So this is based on the same condition there applied, right? And then the loss function, usually you need smooth with just strong convexity and some kind of irrepresentable condition on those f and mu's, not on original sigma. And under these kind of things, right? So you can derive the usual L infinity loss, L2 loss, L1 loss, and so on. So all these kind of things, and then you can derive like sign consistent and so on. So I do not really want to bother you with all these. So I just want to go back and conclude my talk by running the same example again, right? So in this case, I'm not doing principal component regression. I'm just doing traditional, model selection, right? So again, I forecast in 2 years boundaries Premia, so n equal to 2. And then I have 131 disaggregate macroelectron time series. And I use my rolling windows, right? So using 60-month data to forecast the next period. So it's sample size always equal to 60. And our measure is out of sample R squares. I compare a few methods. One is FarmSelect. You are doing lifting, right? So FarmSelect. The other is lasso, directly applied to the data X. And the third one is principal components regression, or augmented principal component regression. So this is the out of sample R square you get. So apparently, our method worked better. And this is forecasting result. It's better for you to see unless you see very, very careful. And more interestingly, when you do model selection, right, so unlike principal component regression, the variable you select, right, you can peek into it and see whether it makes sense or not, right? So here I have FarmSelect method and lasso method. I just compare the the variables being selected, right? And this makes a lot of sense, right? So the first one, most important one, is commodity index price. The second one is BAA, I mean bond versus the federal fund rate spread, right? So is risk premium. And the third one is AAA minus, fundraise, and and so on and so forth. If I want to go detail, you can see which one is more reasonable. And then, of course, I do this not only for 2 years bond risk premia. So this 2-year bond risk premia I put down here. This is out of sample R square, you see, and the number of variable we select on average is about 10. Lasso select more because I decorrelate the variable first, so it's select less variable. And for 3-year bond risk premia, I mean, this story is very similar, right? And 4 and 5. So we select less variables, right? And similarly, now if you are curious, if I use 139, right? 131 plus 8 aggregated macroeconomic time series, and I do penalty only on those 131, right? Because, and so on. And the result is pretty much the same as the table you had before. So in other words, the aggregated, data already being incorporated in our forecasting results. So here is the summary of what I have talked so far. Right? So first, I introduce a very simple, robust prediction methods, which basically say you truncate the data. So once you truncate the data, your sample mean behave pretty much like sample mean from normal distribution, even though you have only second moments. For estimation covariance matrix, your sample covariance matrix is pretty much the same like data from normal. Of course, when you estimate variance of variance is fourth moment, right? If fourth moment exists. And we also show you how to extract latent factors. So because when you do principal components, typically you have augmented information. When you do bioinformatics studies, you have clinical and other information that are available to you or across different platforms. And then third is that we introduce what they call lifting techniques. So by decompose your data into common factor plus equal syncretic part. So by lifting space a few up, right? So you reduce significant biases in model selection because in this case, all covariates now weakly correlated. And of course, we demonstrate the game by theory, simulation, and empirical studies. And if you really like, we have 2 papers here that I just put down here. Thank you very much.